reinforcement learning in vehicle routing problem. And my colleagues were Szymon and Karol, and we were working under the supervision of Dr. Paweł Gora. So the main topic of our project is vehicle routing problem. It's a problem that is based on a well-known problem in computer science called traveling salesman. And the goal in this problem is to design a set of routes for the fleet of delivery trucks while minimizing the total distance covered by them. And finding better solutions is of interest because it leads to even small improvements in the quality of the solutions that are found can lead to great cost savings for transportation companies and in turn increase their profit. But we are not solving the general version, but rather the one with the other constraint on maximum truck capacity, which reflects the real world conditions way better. This version is called capacitated vehicle routing problem, CVRP in short, and it's already much more challenging to solve than the vanilla version. And we also picked this one because other more specific variants of the problem usually are based on this one and contain this constraint. So let's talk quickly about how this problem was approached in the past and currently. So researchers used to create handcrafted algorithms to solve this problem, but they turned out to be limited to a very specific domains. We're quite slow because the problem is NP hard, so it's difficult to find optimal solutions. And those handcrafted solutions usually did not generalize well to the real world domain. And recently, the rise of machine learning-based methods, in particular reinforcement learning, has given new tools to the researchers to find better solutions to the problem. So it has been shown that RL achieves a near optimal performance while being orders of magnitude faster than the classic solutions. And it also can be used to solve problems that include real-world distributions.
So there are two groups of RL algorithms. The first group is algorithms that use heuristics. Two examples of them are the PDP method that learns deep policy using existing solutions provided by heuristics. And the second is neural rewriter that learns a policy for selecting heuristics that solve the problem. And the second group, which we focus most, are purely RL models. And I will describe them now. So the first model is the attention model that uses attention mechanisms to solve VRP problems. On the picture we see encoder that is used to get the points of the trajectory of the final solution of this model. The second algorithm is POMO algorithm. The old way of solving CVRP tasks was taking one trajectory, one policy, and improving the policy based on the one trajectory. But in POMO, we take multiple trajectories and use them at once to improve the policy. And it gets better solutions. And our inspiration of the project is the LG method because it improves POMO. This POMO is improved in the LG method with another policy. It uses normal POMO policy, but it uses one extra policy which is local and is related to node neighborhood. So we did baseline experiments. We evaluated 3 models, which I described, we took 2 benchmark datasets. One was Christofides dataset, which had small instances, and the mean gap, which explains how much solution is worse than best known solutions, was acceptable for all of the models. But on a bigger data set, UHOA, two models, attention and POMO, were not acceptable. Only LG was okay.
Okay, so based on our initial results, we choose POMO to be a model that we want to enhance. Why? Because as the authors of the paper said and mentioned, that not every starting node in the CVRP is the best optimal, it will be the node that will start the optimal trajectory. For example, on the slide, we have the best optimal trajectory for a RL agent that will choose the next node as counterclockwise. So we have only 3 nodes that are the best starting nodes for this, for optimal trajectory. So what we wanted to do, we wanted to add a lightweight RL agent model that will choose a good subset of initial points. So that was our intuition behind this. And in the original POMO, they choose all clients as the starting points, and we wanted to choose only K clients. So how we did it? We applied a lightweight RL agent to select points using multi-head attention and feed-forward network. And these selected points are, for example, let's say we have an instance, we have a problem, we have an instance of a problem of the size 100, and we want to choose 20 starting points. So we are creating 100 trajectories as in POMO. However, we are choosing only 20 starting, 20 starting points. So for every starting point, there are five trajectories. We trained this model alongside the POMO, and we trained it using the auxiliary laws that was based on reinforce, and using probabilities in the from the output of our model, using Gumbel softmax in training, and using softmax in inference. And the whole model was implemented in RL4KO library, which is a library that contains framework to train CVRP model and other models that uses reinforcement learning for combinatorial problems. It's also worth to mention that this model was trained alongside the POMO, and we updated our RL agent every 100 epochs with accumulated gradient from this, after 100 steps, sorry, not epochs, with the accumulated gradient. Okay, so we trained our models on 3 different problem sizes, which was 20, 50, and 100. And for each case, the model chooses 20% of all possible nodes as starting nodes, which was 4, 10, and 20 accordingly. We also evaluated GAP that was mentioned earlier on CVRP-lib. That is a benchmark dataset that contains problems that varies in size and distribution. It also contains contains datasets UCHOA and Christofides that was mentioned earlier. Okay, so let's see the results. So we have on the plot we've seen that on the x-axis we have number of steps, on the y-axis we have the validation reward. In our case, we want to minimize the cost, so the validation reward is the negative value of the cost. So if the higher the value, if the higher the reward, the less the cost. The yellow line is our solution, and the blue line is vanilla POMO original model. And as we can see, our model converges faster and achieves better results than original POMO on 20 locations. It also happened on 50 locations. However, the gap was a little bit smaller. And as we can see, as the number of our number of clients increases, the gap the gap decreases, the percentage gap decreases. Okay. Also, let's see the validation results on the CVRP-lib. We have the bar plot, and on x-axis we have the bins that we divided the problems by the number of clients. Okay, and on the y-axis we have average gap. As we can see that our model scales better on the larger instances. However, the performance on the average gap that on the models that were trained only on the problems that were trained in 20 number of clients has not very good results. The average gap is higher than 1. Okay. However, on the 50 locations, the results were significantly better, and also we can see that our model scales better. However, on the 100 location, on the problem instances as higher than 150 customers, our model achieved better results. However, on the problems that we trained model, which was 100 locations, the model our solution achieved a little worse results. We think that we should study how number of customers would affect the performance, and we also think that both models are a little bit undertrained due to the fact that number of locations is much higher. Okay, so what are the conclusions of further work? So our improvement to the POMO model proved that the smarter selection can improve model performance. It also proved that it can also enhance the scalability of the existing model, and there's a room for improvement and adding this method to POMO-based solutions such as ALG or OmniPOMO and other models that are based on POMO. So thank you all for your attention, and are there any questions?
Do you have any questions? I'm curious whether you analyze example solutions that you found, and like how did they look like, and
like how did the model choose the? We haven't because the number of instances was very big. The distribution of the points were different. However, we haven't studied a lot, deep dive into how the solutions overall looks. We choose only how the cost of the solution is.
Questions? Well, then, thank you once again.